Welcome to my presentation. My name is Gosch and I'm doing my PhD in Material Science and Testing of Polymers at the Montanuniversität in Leoben, Austria. And today I want to present methods for automated crack length detection in fatigue tests of unreinforced polymers. So why is this topic so interesting? Because methods from the field of metals are not used in the case of polymers because it's not possible most of the time. And it's still state of the art to do the crack length detection during fatigue tests manually for polymers. This means by the use of a microscope. Therefore, the automation of this process is really interesting, which brings me to the introduction of my presentation. In the introduction, I wanted to answer two main questions. First of all, why is the crack growth behavior of interest? Because of lifetime estimation for component design. So lifetime is the time between installation and failure of my component. And it is very important to know this lifetime for all kinds of developments. The second question is, why fatigue tests? Because it's the most detrimental loading. So lifetime estimation using fatigue fracture mechanics determines the worst case scenario. How is the lifetime estimation done? First of all, you need a specimen with an initial crack length, and you load the specimen with a fatigue loading. During your experiment, your crack length increases, and you can calculate the crack growth kinetics curve, where the crack growth rate, dA over dN, depends on the loading, in this case, the stress intensity factor. The crack growth rate is determined directly from the specimen and the determined crack length, which is measured directly during the test, and the loading is determined from the applied fatigue load and the geometry. Based on this crack growth kinetics curve, you can calculate your lifetime, a lifetime model. The main focus of my presentation is the crack length measurements to evaluate the lifetime. And as I mentioned before, it's still state of the art to do this manually, so with the help of a traveling microscope. And therefore, you only get a limited number of data points during your measurements, and sometimes there are difficulties in the detection of the crack tip. Therefore, automatic crack length measurements are getting more and more interesting in the case of polymers. In this work, we used two methods, two automated methods. The first one is based on digital image correlation, and the second one on infrared thermography. This brings me to the content of my presentation, where I want to present you the experimental setup which was used in this work, then the results from the microscope, the digital image correlation and the infrared thermography, and finally a short conclusion. Now I wanted to present the used experimental setup. For the fatigue tests, an MTS testing machine was used, and there were three setups. The first one is a microscope versus a microscope to determine a standard deviation for the measured crack length. The second one is a microscope versus infrared thermography, and the third one is a microscope versus DIC. The used specimens were sharp-notched CT specimens, and we tested three different kinds of polymers with different mechanical behavior: a PVC, a PMMA, and a POM. Because of lack of time, I only wanted to present the results from POM. This brings me to the first results from the microscope versus microscope setup. The first setup, microscope versus microscope. Here in this picture you can see the experimental setup. The specimen and the two traveling microscope installed close to the testing machine. As you can see, we measure the crack length on both sides of the specimen to determine a standard deviation. This is especially important because it was not possible to install the automated method and the traveling microscope on the same specimen site. Now let's go to the testing procedure. First of all, we load the specimen with a fatigue load, then we stop the fatigue test, apply a constant load, and we measure the crack length with both microscopes on each side. And then we start again until a complete break of the specimen. Now we move to the second test setup, the digital image correlation. Let's move to the second setup, the microscope versus DIC. Here you can see the testing setup, a DIC camera on the one side and a microscope on the other, and in the middle the specimen. Concerning the detailed testing procedure, we start with a fatigue loading, then stop the fatigue test, apply a constant load, and then we measure the crack advancement on the one side with the microscope and on the other side with the DIC. During the DIC measurements, we faced some problems with the displacement and elongation fields. First of all, the crack tip position determined via DIC and the real crack tip position, which is inaccurate in some kinds. In the second one, the field from the DIC is displayed holes in the surface when the crack opens or some flanking appears. The evaluation of the crack length using DIC. First of all, two parallel lines close to the initial crack tip were made, and the distance between these sections was measured continuously. As a threshold value which correlates with the crack tip, it was not possible to use a constant value, and a good correlation between the inflection point of the displacement and the actual displacement of the crack tip, so the crack advancement, was found. Therefore, the displacement over the length of the section was determined for every picture, and the inflection point or reflection point is now correlating with the crack tip position. Finally, the third method, the IRT, infrared thermography. The third setup, the microscope versus the IRT camera. In this picture you can see the experimental setup, the IRT camera, the microscope, and in between the specimen. And the testing procedure was somehow similar to the ones before. First of all, we apply a fatigue loading. Then we take the IRT picture, so before stopping the fatigue test. Then a constant load was applied, and we measure the crack advancement via the microscope. Here it's really important to do the IRT picture before stopping the test to determine the crack tip close to the hottest point on the specimen surface. Here I wanted to present you the evaluation of the actual crack length via the IRT camera. You can see a CT specimen with the hottest point here close to the crack tip, and we measure the ligament length from the backside of the specimen to the hottest point, and we can evaluate the crack advancement. This brings me to the conclusion and the outlook of my presentation. Finally, I want to give you a short conclusion about the measured average differences in the crack length. Here you can see the three test setups which were used, so the microscope versus microscope, the microscope versus IR, and the microscope versus DIC, and the three polymers, so the PVC-U, the POM, and the PMMA. And as you may know, now the crack lengths were determined on the front and the back side of the specimens, therefore we got an average difference. And now I wanted to present you the results. As you see, there are differences within the polymers. So for PVC-U, the largest differences were measured, then POM displayed the lowest, and PMMA is in between. This is because of the mechanical behavior of PVC-U compared to the other two. PVC-U shows large plastic displacements and huge plastic zones in front of the crack tip. Therefore, the crack length determination is somehow a bit more difficult, and the differences were larger. But all in all three methods display really low amounts of differences, so all of them were close or below 5%, which is really a good result. And based on this determined results, we can now go a step further to do our automation. Finally, I want to thank you very much for your attention, and I'm really open for questions, and you can also write me your questions here. I show my email address. Thank you very much.